Hi, this is Open Up Resources, Algebra 1, Unit 2, Lesson 9. I can see, can't you? We're going to practice understanding and finding the average rate of change of a function in an interval. And we're going to develop a formula to help us find that average rate of change. So, Kwan's parents bought a home for $50,000 in 2007, just as real estate values in the area started to rise quickly. Each year, their house was worth more until they sold the home in 2017 for 309,587. So, um, how we're going to do this is first we're going to model the growth of the home's value from 2007 to 2017 with a linear and an exponential. Okay, so two different types of graphs. Actually, do linear in green and exponential in blue. And so that way we can kind of keep them separate. One thing I'm going to do first, though, is I'm going to draw my graph because I know I'm going to need to go to over 300,000. And instead of going by 2007, 2008, 2009, that type of thing, I'm going to go year after 2007. So 2007 is going to be my year 0. And then I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I don't need a whole bunch from there. And on the way up, I'm going to go 50, 100,000. So this is dollars in thousands. 150, 200, 250, 300, 350, 400. Okay, so if I just plot what I have, I'm starting 2007 with 50,000. And then in year 10, I'm going to be a little over 300,000. So I'm going to go ahead and connect this as a line going through here, like that. So there's my linear model right there. So to find my linear value, I'm going to subtract my two y's. So 300, back to drawing, 309,587 minus 50,000, which is actually 25,905, 259,587. And then I need to divide by the 10 years that we had that going. And so that's going to equal 225,958.7. So to be able to do my linear model, I'm going to say f of n equals my slope, which is this over here, 25,958 n. And then I need to add my 50,000. That's my y-intercept, right? The y equals mx plus b. My slope, 1,000. Oh, I forgot the point. 7 in there. So now I'm going to have my Desmos up too. I'm going to go ahead and put this into my Desmos. Control C. And that way we can see how this looks. And I'm going to switch my settings. So I want to go from -1 to, let's just do 15 to give us some space. And the y-axis, since we need to go by, let's see, we did 50,000s on our other one. So let's go negative, I'm just going to do 0. And then we need to go up to 350,000. We want our increments to be, what did we do? Do 20,000s on here? Oh, what's wrong with this? Oh, I can't use commas. That's right. Okay, there's my line. I'm actually going to zoom out just a little bit so I can kind of see my line right there. And maybe adjust it there. That's kind of where I want that. Okay, so, and one thing I'm going to do with this, I'm going to go to my settings and I'm going to create a table with it. And I want to go 0, 1, 2, 5, and 10. Oh, 10. Okay, so I can see that my numbers all work out on this table, so I can kind of see that, yep, they're all on that line. For plotting it, okay, so I'm going to go back over here, and now I'm going to do the exponential model. Now here's the catch kind of with the exponential. Sometimes with these bigger numbers and more complicated things, we have to round to be able to do our roots, right? Our 10th roots. So let's go ahead and just write our equation, and then we're going to have to tweak it from there. So I start with 50,000, and I'm going to multiply it 10 times by my common ratio, and I need to end up with 309,587 on there. So I'm going to divide out my 50,000. And so r to the 10th equals a 6.1417-ish number. And so when I take the root, the 10th root, I actually get r equal to 1.45 when I do that. So that would insinuate my model. So I'm going to go ahead and just type what I'm doing here. And we might have to tweak it because, as I said, when we have to round, that starts affecting a lot of our stuff. So when I type that in and take the root, I end up with 1.45. So f of n equals, and then we have our 50,000 times 1.45 to the x, right? Because we start with the 0. So I'm going to put this into my Desmos for another one. And we're going to add a new expression. F of x equals equals 50,000 1.45 to the x. Okay. So that gives me, that makes it cross down here. So I'm going to go ahead and do a table for this so I can kind of see what my values are. So again, I'm going to do 0. What is wrong with this? Here, we'll do this as a y equals, and make this y equals. Okay. Okay, we'll turn this into a table. All right. So if I put in 0, like what's going on here? 1, 2, 5, 10. So if you see that at 5 years, I've already surpassed my 300 and I want to be back here. So I'm actually going to tweak this a little bit. Just do the 1.4. That's getting it a little bit closer over there. Let's do 1.3. Okay, so this is where it's nice to have the Desmos because that rounding at the 10th root is so, you have to go so far down to make it accurate that it sometimes is kind of hard on here. So that was still too high. Ooh, 1.2, look at that. That is really close to our point, 3.9586. Oh, we need 3.5, 309, 587. So we need to tweak our equation to be a 1.2 on here. Okay, so when I graph that, I have some points at 1 is 60,000. So I'm going to go ahead and plot that on here. 1 was a 60,000, so it's about 50, that'd be 75. So it's between those guys. So I'm going underneath here. And then 2 was 72. So that's a little bit, I don't like how that blue one's really high. Okay, so 56, I cannot get this accurate with my, all right, I'm going to use the cursor and see if I can get a little more accurate. So 60 right here. 72 is going to be just under here. And then what was another one? 5 was 124. So 5 was right at that. That's 150. So 124 would be right about here underneath that. And then 10 was up here with the 309. So if I were to connect these, I'm going to go whoop. See how there's kind of a curve involved in here. All right. So what was the rate of change in the home's value from 2007 to 2017? So the average rate of change is change in y divided by the change in x, which is really a slope, right? I'm just going to put over here, same as a slope. So if we really look at those 2 points, 2007 and 2017, our average rate of change is going to be the same for both, isn't it? It's going to be that 259 or 25,900. Wait. Oh, what is the change in the home's value? So the change in the home's value is just the subtraction of the two. It was the 309,587 minus the 50,000, which equaled the 259,587. So the change in value was the 259,587. All right, so that was the answer to number 2 here. So the average rate of change is defined as kind of what the slope is. So what was the average rate of change of the linear function of 2007 to 2017? Here's where I want to put that slope. What was the slope there? 25,958. 958.7, right? And what was the average rate of change of the exponential function? Well, if we go from those 2 points, it's still the 309,587 minus 50,000 divided by the 10 years, which is the 25,958.7. So the average rate of change, just to clarify, the average rate of change is basically the slope between those 2 points, right? So how does it change? How does that average rate compare between the 2 functions? Well, it's the same, right? Because they are the same, because both functions begin and end the same values, right? We're starting in 2007, 2017. So now, what is the average rate of change of the linear function from 2007 to 2012? So if we go to our Desmos, and I'm going to go to my first one here. So 2012 would have been 5 years. So that's our 5-year mark. I already put those in. Nice. 179,793. So I want, you know what, I'm going to just keep with the text box. So this is our linear. Let's do it in green. It was 793.5. 793.5. So that's our year 12, and that's minus 50,000, our original. There, and put a comma. minus the 50,000 equals, here, so 179,793.5 minus 50,000 equals 129,793, 129,793.5. And so if we divide that by 5 equals, right, we're finding our slope. That back up. Divide by 5. Oh, look, it's our slope, right? And does that make sense? All slopes should be the same on a linear equation, right? 25, 9, 8, 7. Okay, so it's the same. So now what's the average rate of change in the exponential function in the interval from 2007 to 2012? Well, if we look at the exponential, its 5-year is 124, 416. So let's go in blue on this one. 124, 416 minus 50,000. Just make sure I wrote that right. 124, 416. Yep. Okay, so let's go ahead. Equals. So if I do 124, 416 minus 50, so 74, 416. 74, 416. And then I need to divide that by 5 because it's over a 5-year period. Divide by 5. 14, 883.2. 14, 480, 882.3. Was that right? Oh, 83.2. 88. Got this backwards. 2. Okay, so notice how my rate of change was different. So how do the average rates of change from 2007 to 2012 compare in these two functions? Well, if I'm going to compare these guys now, the average rate of change, the exponential function is less than the linear function. How? Because the home value predicted by the exponential function. And let's see where it falls on the line. So if I look at year 5, which is right here, let's get this up just a tad. There we go. So this is year 5. Notice how the exponential function is lower, which makes it a smaller slope if we're going straight across here as opposed to straight up here. So that is a less steep hill, so that is a smaller slope. Exponential function, home value is less than the linear function in 12. Okay, so that rate of change is different depending on your points when you have an exponential function. Okay, so how can you use the equation for the exponential function to find the average rate of change over a given interval? How does this process compare to finding the slope of the line through the endpoints of the interval? So how do you use the equation of the exponential function to find the average rate of change over a given interval? So you use the equation to find the value of the function at the beginning and the end of the interval and divide by the length. We have to have a specific interval on there. So how does this process compare? It's the same process. It's finding the slope of a linear equation or between 2 points. Okay. Graph the slope of a linear equation. I'm going to put in here in slope intercept form. Or between 2 points on a graph. And so that equation, what that looks like, let me go ahead and just kind of write in here what we're talking about. So that equation is when you have the interval of a to b, then the equation is the function of b minus the function of a over b minus a. Same as the slope. y1 minus y2 over x1 minus x2. The change in the y's over the change in the x's. Same idea. All right, let's go ahead and kind of keep going with this. So consider this graph. What is the equation? All right, well, if I look on here, I see a point. I'm just going to do a quick table here. I see at 0, we're at 1. And it looks like, you know what, I'm going to go backwards on here. 2, 3, 4. I'm going to put 0 right here. And at, looks like at -1, 0, I'm at 1, -1, I'm at 2, -2, I'm at 4. So it looks like I would be at half here and 1/4 here. So seeing that I am multiplying by 1/2, I think my function would be f of n equals 1/2 to the x power. What's the average rate of change from -3 to 1? So I'm going to go ahead and graph this on my Desmos, and I'm going to close all those out. I'm going to go back to my original graph with this and kind of put it in a little closer. So f of x equals, and I'm going to do 0.5 to the x. Okay, so that's my same graph. And now I'm going to do, let's make a table out of this. And let's go ahead and just put in some of these points that they're saying. -3 to 1, 0, -1, and 1.5. Okay, so I need -3, -1. Here I need a -1.5. Oh, I did those backwards. 5. Here would be the -1. And then 1, 2, and let's do 3. Okay. I don't remember if we needed to go to the positives. Oh, it's just 0 to 1. All right, that's okay. All right. So at -3, we're at 8. And at -1, we're at 2. So I'm just going to go ahead and fill in some of these numbers. So that's 8. And this one was at 2 at -1. At -1.5 was 2.828. So 2.828. 0 was at 1. Oh, we already did that one there. 0 was at 1, and 1 was at 0.5. So 0 was 1, and that is 0.5. So I'm just going to go ahead and fill those in. So I have this on here. So rate of change. Let's go ahead and fill some of these in. So my rate of change is 8 minus 0.5, which equals 7.5. And I need to divide it by 3 to negative 3 is 1, 2, 3, 4. So I need to divide it by 4. And that's going to equal, let's see, 7.5 divided by 4 is 7.5 divided by 4, 1.875. 1.8. Okay, so now for this one, I'm going from 8 minus 1, which equals 7. This time I need to divide by going from negative 3 to 1. So that's 1, 2, 3. Oh, to 0, sorry. 1, 2, 3. So that's divided by 3. And so that's going to equal, divided by 3 is 2.3 repeating. 0.3, and we'll just round. Okay, so here for this one, I'm doing 8 minus 2. So 8 minus 2 equals 6. And here from negative 3 to negative 1, 1, 2 is 2 spots. Well, 6 divided by 2 is 3. So that was an easy one. And this one, I'm doing 8 minus 2.828, which equals 8 minus 2.828, 5.172. 5.172, and I divide it by, let's see, so it's 1, 2, no, 1.5, right? So that's not how I, so 1.5 equals 1.5, 3.44, so let's just say 3.45. We'll round to the tenths or hundredths. 3.45. Okay, so draw the line to the points at the beginning and the end of each intervals in 11, 12, 13, and 14. What is the slope of each of these lines? Okay, so negative 3, we'll do the first one here in purple. Negative 3, 8 is about right here. So this is the first one. It's making a nice little dot there. And I need to go to 1, which is 0.5 right here. Okay, so I'm going to go ahead and get my line. And I'm going to connect this with this. Okay. And then my next one, let's use green for it. We'll do, this one will be the green line. This one was the purple line. So this line is from negative 8 to 1. So negative 8 here, down to 1 right here, with a 0, 1, 0, 1. All right. This one, let's turn it blue. This will be from negative 3 to negative 1. So up here to negative 1, which looks like it's right about here. And then negative 3, one more, we'll do yellow for this one. Negative 3 to negative 1.5. So negative 3, 1.5 is probably about right there. Okay, so about right there. All right. Might have been a little high. Anyway, those you can kind of see the different lines on there. So what is the slope of each of these lines? Well, I'm just going to write in this one, same as the rates, average rate of change listed above, right? That average rate of change, except, are these positive slopes? No. Except negative. negative. So 11 is a negative 1.875. 12 is a negative 2.33. 13 is a negative 3. And 14 is negative, 3.45. So I'm going to scoot that up just a little so we can see. All right, so that's kind of our rates of change on there. Almost done here. So which of these average rates of change best represents the change at the point negative 2, 4? So right here, negative 2, 4, the average rate of change right there. Explain your answer. Well, if you think about those different lines that we had going on here, which of these lines crosses at this point pretty close? It would be our orange one. So that would make 3.45 our best guess in this case. 3.45 because that line is the closest to approximating the curve of this interval. All right, so how does the average rate of change compare to the change factor for an exponential function? What is described by each of these quantities? So the change factor is your common ratio. So how does this compare to the common ratio? Average rate of change is not the same as the change factor. So for a given interval, change factor tells what to multiply with the y value to get the next one. At the end of that interval. Average rate of change instead is the difference between the two values. That's like our slope. Here's slope. And it's linear. But slightly different. Okay. Are you ready for more? We'll swing by this one real quick. So, what does it say? It makes sense to some people. The way to find average rate of change of a function would be to find the rate of change at the beginning of the interval, the rate of change at the end of the interval, add the two rates together and divide by 2. Does this work? No. It only works with linear functions because the rate of change is constant. It's incorrect otherwise. Okay, so average rate of change of a function, here's our takeaways, over the interval a to b is, so is that f of b minus f of a, so the answers to each of those, minus b over a, or divided by b over a. So what this formula means is find the value of the function at the beginning of the interval and at the end, then divide by the length of the interval. So value at the beginning and the end, and then divide by the length. And secant line. Let's just review what a secant line is. A secant line is, let's do this one in green. So we didn't actually say that, but that is what we were drawing to find the average rate of change. This is the line that contains the endpoints of the curve on a given interval is called secant line. So, and the endpoints on the curve. So what we drew up here is we drew multiple secant lines, 1, 2, 3, 4 different secant lines between those points. Our linear here, this was a secant line, our linear function. All right, thanks for joining us today, and we will see you next time.